The reason I'm sharing this presentation with you guys is to share the expertise that we have learned on building applications and deploying them in our testbed and how Docker has been beneficial for us. So the outline of the presentation is going to cover the first thing is why do we use Docker? What is the terminology that's associated with Docker? And then I'm going to briefly show you a tutorial on building a simple web server. And after that, we're going to see how Docker can help us in our research. And the last thing is a tutorial on packaging images for deployment on the CARLETON-CISCO testbed. So the first thing is when we look at Docker and why Docker, we have to look back, first of all, at how traditional applications used to function. In traditional application, we used to package all the scripts and all their dependencies into one single block. And this single block might have different libraries which have incompatibility in versions, they have different dependencies, and they are built for one single operating system. Now, in this scenario, many things could go wrong. For example, the OS could get an update or get a security patch, and suddenly my code crashes and I don't know why. Or it could have incompatible libraries, or it could have incompatibility in dependencies. So to break this problem, Docker comes in to solve it by introducing some of modularity into the code. But before we jump into Docker itself, let's look at what's inside a computer and how a computer architecture looks like. So a computer is based on hardware, software that is encapsulated in an operating system, and the hardware could be CPU, RAM, storage, network, any resource that is in a physical computer. We use something called a kernel to interface between hardware and software. Now, any application that is built on top of an operating system would usually have to go through the operating system, then through the kernel, then access physical resources. This forms a bottleneck, and in order to counter bottlenecks, container technologies come in as a solution to package applications with all their dependencies and all their libraries in an isolated environment. And this isolated environment is able to interact with the kernel directly without having to go through the operating system. By doing so, by not going through the operating system, now we are independent of any operating system. Because containers are based on Linux kernel technology, and Linux kernel technology is available in most operating systems that are based on Linux or Unix, like Macintosh or Linux Ubuntu distributions, even Raspberry Pis. This enables us to deploy whatever application we code on our computer. It is guaranteed to work on any of these operating systems. And recently, Windows also added Linux kernel support. So this means that we can run the code we write as a container on any of these operating systems, including Cisco routers and switches. And we're going to show you how we can deploy these things on Cisco routers and switches. Also, the cloud services, Google, Amazon, and Azure are all moving into a serverless architecture where you don't actually rent a physical host. Instead, you choose a service and they decide where to place the service based on performance constraints, which is based on lightweight container technology. So the advantages of Docker, by breaking down the code and the dependencies into small containers, lightweight containers, this solves the problem of it works on my machine, but when I deploy it on other machines, it crashes, and we don't know why. It also allows reuse of application components by breaking them down into microservices. Each microservice is based on something we call a base image. The base image has the basic tools or basic libraries necessary to interact with the underlying hardware, and then we inherit images from the base image to create different versions of the modular application that we are building over time. In terms of testing, it is easier to identify source of errors because we have a modular design. We can directly pinpoint each component, and because each component is smaller now, instead of thousands of lines of code, only tens or hundreds of lines of code, it's easier to test each component individually and make sure it works before we deploy it in our complete system. In terms of maintainability, if a single component breaks, it doesn't break any other component that is in the system, and this will be only individually affected. Also, we can update a single component alone without affecting the entire system. Some basic terminology we need to understand before we can jump into a tutorial on Docker. What is Docker? Docker is simply an open source tool that automates the deployment of software applications that are inside containers by providing them an additional layer of abstraction. And this abstraction, unlike a virtual machine, it is an OS level abstraction. OS level means it can directly contact the kernel to get services like storage, network, CPU or RAM for processing. The next thing is provided by Docker itself is Docker Hub, which is a repository hosted online. It's for finding, sharing container images. It also allows you to work with your team and collaborate in private repositories. But otherwise, it's an open source market for you to find these ready-made containers and build on top of them your applications. The next thing is Dockerfile. Dockerfile is nothing but a simple text file. It's a few lines of code that have instructions on how to build an image and where to get the base image from and what things to copy inside this container environment. An image is a lightweight standalone executable package. Basically, it's an encapsulation of everything we need, including our script, our dependencies, services, in something very, very lightweight. It could start from a few MBs up to a few hundred MBs, unlike virtual machines which go for gigabytes. And after we have created an image, to run an image, we call this container. Container is simply when an image moves from our hard disk onto our RAM to operate in runtime. This is called container. So now I'm going to jump into the tutorial so that we understand how all these terminologies and all these technologies work together. In this simple tutorial, I'm going to create a web server. This web server is a very lightweight web server based on something called Nginx. And basically, I'm going to create an index.html file, which will have my landing page for the web server, a Docker file, which will have instructions on how to create the image using Docker, which is a toolbox to use containers. We will use the build image command, which will take this Docker file, copy the necessary dependencies, install the necessary libraries, and create an image called Simple Web Server. After we have created an image called Simple Web Server, which is only a few megabytes in size, and we're going to see it in the demo, we are going to call the run command. Run command takes an image that is in on my computer and is not active, and the moment it becomes active, it is now called a container. So a container is the runtime environment for this image. I'm going to show you how we can run two different images or two different containers of the same image by operating at different ports. So it's like running two web servers on my machine. So let's jump into the tutorial now. And the tutorial is based on command line. Docker is based on command line. And in this command line, we're going to create a new directory and browse to that directory. We have to work in a working directory. So I created on my desktop a folder called Docker tutorial, and I have to browse into that Docker tutorial folder. Step 2 is to create the application logic. Application logic here is simply the index.html file. It's a very simple HTML file that has 2 lines. Welcome to Internet of Things Lab. And the next line would say, this is a lightweight server based on a container. So after we have created this HTML file, it is important to save it in the same working directory that we have just created, which is on my desktop called Docker tutorial. The next step is to create the Docker file. Now the Docker file is simply starts with a keyword from. From is simply me saying where my base image will come from. So in this scenario, my base image is called Nginx stable alpine. What this means is we're only working with a stable development environment based on Alpine Linux, which is a very lightweight version of Linux, and this has the Nginx web server. So somebody in the community on Docker Hub has published this, and this image is just me using it by simply using this command from Nginx stable alpine. Now, if I want another operating system, simply I can just change this. If I would like to run my web server on, let's say, Ubuntu or Windows or anything else as an operating system, because of its built-in tools and services that come with that specific distribution of operating system, I can simply change this line. The next thing is for me to copy files into the virtual environment. To copy files, the format is we start with our file and then we go to the working directory. So for Nginx, the web server, to work, we have to copy our index.html file into the usr share Nginx, which is a working directory for the Nginx folder. And this Docker file that has my instructions will also go into the same working directory that I have previously created. Now, basically what happened in that from command is it took a base image called Scratch. It's all happening in the background and we don't see it. Then on top of Scratch, it took it from that, it inherited an image and created something called Alpine 3.10. On top of that, it got an image called Nginx stable Alpine, and this is the custom image that I have just created called simple server image. Inside simple server image, I add my index.html file, which will run the entire stack. And all this stack as a container package will interact directly with the Linux kernel. Now, the next step is to build this image from the Docker file. So we're going to combine these two and create an image called simple server. To do this, I'm going to go back to my working directory. Now after I have created those two files, now I can see that I have my text file, Docker file, and the index.html that contains 2 lines of hello world text. Now the next thing we have to do is for us to run the command docker build. Docker build builds an image, and the syntax of this command is to docker build and then followed by a tag. Tags are not necessary, they are optional, but with tags we can easily locate our images if we have multiple. So my tag is simple server. The dot after is simply indicates the location where I want to place the built image, which is in the working directory and is represented by a simple dot. So now it goes ahead and pulls these layers. These layers that it just pulled, 1, 2, and 3, are Scratch, Alpine, and Nginx. They are now in my library. If I need them for later use, I can simply reuse them. And this is the modularity in container technology. So what it did next is step 2, it copied the files into the container, and now my image is ready. Now to show images, we run the command called show all Docker images. Docker images will show me all the images. Here is my simple server, which has an image ID, a hash value. It has been created 6 seconds ago and has a size of 20 megabytes only. So this 20 megabytes can be seen as a complete virtual machine of size only 20 megabytes. Other thing it added was the Nginx image, and this Nginx came from Stable Alpine because of my keyword from Nginx Stable Alpine. Now the next thing we want to do is to launch the container. And to launch the container, we run the command docker run. In docker run, what we are doing is taking this image and creating a runtime environment from it. The syntax of this command is simply docker run and image ID or image name. So here we can see the image ID is this hash value, or I can simply use the name I just gave it. One more thing we have to note is because this is a machine and we have to run this machine on top of another machine, we have to do some port mapping. And this port mapping has this format. We use the option -p and we choose my machine port, the port incoming, to the port outgoing into the container. So as you can see here, my command was docker run -p 8080 and I'm using simple server. This created the container. Now we're going to see how this container is running and how do we access it. Simply to check the container that it's running, we go to localhost and here is my index.html file. Basically, it says, welcome to the Internet of Things lab. This is a lightweight server running on a container. This is my web server representation, which I can, because I'm accessing it from the same machine, I'm using localhost. If I want to access it externally, I can simply put the machine's IP, the port that I just specified 80, and it will map it to this container. Now we want to check the status of the container and launch another container. So to check the status of my containers, we can run the command docker ps -a. The -a flag shows me all the containers that are running and the containers that have been stopped. Now, what we see in this view is we see a container ID. Each container has a unique ID. It's based on some image, which I just created called simple server. The command that gets executed the moment the container launches is basically Nginx, run it in the background. And Nginx is simply a web server, so it's offering me a web service on port 80, and these are the ports we can see. So it's hosted on localhost. This is why the IP is 0000. The mapping happening here is from port 80 inbound to port 80 outbound TCP connection. Now, to launch another instance of the same image, I can simply run docker run command. Now I'm giving it a name. I'm giving my container a name and choosing the ports again. Now, because container 1 is running on port 80, I cannot launch it on port 80. I have to launch it on another port. This is why I have put my inbound connection on my computer to be 81. So if I choose 81, it will take me to container 2. Let's give it a try. So now it's hidden behind this bar, but I chose 81 and this is being served from 81. And as you can see, the web server logs this connection here on the console output. Now, the next thing we want to do is we want to look at how we can manage containers, how we can start, stop, remove containers, and how we can remove images. So for us to, if we have a container, it will continue running unless it has completed its task. So containers are designed to be very lightweight, to do one specific task and then go into idle mode. Idle mode means the container stops. Because it's very lightweight, as you can see, it launches within seconds. And for me to stop a running container, because it does consume system resources, I can run the command docker stop, and I can give it a container ID or a container name. As you can see here, I have two containers. So the first container created got a random name, objective feastil. This random name was generated by Docker engine itself because I didn't specify a name when I created it. So I have to refer to it by using the container ID or the random name. However, for the second container, when I created it, I did specify a name. This is why I can easily identify it, and it is recommended for you to choose pretty names rather than having the random names generated by Docker itself. So for us to stop a container, we simply run the command. In this option, I chose to stop it using the container ID. And after running the docker ps -a command that shows me the list of all containers running in my system, I can see now that the container here exited and this container is still up. So I have to do the same thing for the next container and stop it. And now all containers have stopped. So the starting and stopping of containers is fairly fast, it's fairly quick because of the lightweight technology. Now the next thing we want to do is deleting a container. To delete a container, we use the command docker rm. So it's very simple. Docker ps to view, docker stop to stop a container, docker start to actually start a container, docker rm removes a container in the same logic that we used here, in the same syntax. So now I'm going to delete those containers that have been stopped. And the next thing I have to do, because those containers are dependent on an image, I am unable to delete the image that I just created unless I delete my containers. And now for me to delete an image, I use the same syntax, docker rm, but I add an I for the image. Again, I can delete it by image ID or image name. Image name is simple server, image ID is the hash you can see here. And now the container has been, the image has been cleared from my system, and after I run the docker images command, I won't be able to see the simple server. An alternative to container management is a GUI-based container management that has recently been added by Docker in the latest update. So in a GUI-based environment, you are only able to, so you can go to the Docker engine and choose dashboard. In the dashboard, you can access the image using your browser, like what I just showed. And the next thing you can do is you can access the command line interface. So the command line interface is interesting because the moment you deploy this server, it's like accessing a remote server on AWS, for example, where you need to open an SSH session into the container. And we're gonna go through that in a bit. We can also stop containers, we can restart containers or delete containers, but we cannot access images through the GUI. This is why it's better for people to go through the terminal, but for non-experts in Linux, this is another option to access and manage your containers. So now I'm going to access the command line interface of the container that I just created, which is based on a Linux Alpine image. As you can see, it's a normal terminal with all Linux commands working regularly. Now I'm browsing into the directory that I just created, and I put in it the index.html file. This is where my web server is serving me my web page, and I can edit it through terminal. If I want to do any changes, I can do that, or I can run simple Linux commands like finding the IP address of this container so that I can do networking or do other stuff with it. Or if I want to add my scripts here, I can easily add my scripts. This is a complete machine. For people who are not familiar with terminal, one option is to add, for example, something we call a VNC server for you to stream the screen like TeamViewer, or like you would in TeamViewer, and control it like a GUI as if this computer was here. But it's not a computer, it's a very lightweight version of a computer. So that was it for the tutorial on simply building web app or a web server. The next thing we're going to look at is how Docker helps us in research. So research is a very fast-paced environment where things change a lot and the requirements might change a lot. Therefore, in a simulation environment, one might write his code on his laptop or his personal computer, but realize that he has to scale this to multiple nodes. If you're developing, for example, a distributed environment, you might want to scale it, or you might run into performance issues with your current system and you want to move your code into another system, a more powerful and resource intensive system. Or you could be testing other algorithms in the literature. Or you could be building on top of a colleague's work. Now, in a traditional way, you would have a script, have to set up the service, have to set up the libraries, have to set up the dependencies. This alone might take you weeks, especially if it's someone else's code, someone else's algorithm. It's going to be very hard to understand all the dependencies, and you're going to face a lot of errors without understanding what the source of these errors are. Instead, we take the script that we have, which we know what the dependencies could be for the script. For example, if I'm using machine learning and I need the TensorFlow library, I can simply get a container that has the TensorFlow and has all the dependencies I need and run my script. And this container can be fetched from the open source community, from Docker Hub, or from GitHub, or I could write my own custom image. Now, as you saw, running a container, a simple web server, which got fetched, I didn't have all the layers, they got fetched from the internet. It happened within seconds. And this is the major advantage of using Docker in research, because sometimes we might want to try an algorithm rather than implement it right away. Try and see what results it produces. And this is a very quick approach for us to just skip through all the unnecessary details and run the script and see what results it produces. Another approach could be a hardware deployment. For example, in the Cisco project, we are deploying the algorithms we write on multiple layers of the testbed. In this testbed, we have different operating systems running and different capabilities of devices running. If we have to deploy this on a massive scale, for example, on our 30 Raspberry Pi infrastructure, this will take us an extremely long time to deploy it. Or to deploy it on the IR829, it has a Yocto operating system on it, which is a Linux operating system. If we were to design the script to run on this specific environment, it would take us weeks, maybe months if we run into challenges. Instead, by using Docker technology, we are able to deploy it on any of these layers, on any of these operating systems, including Raspbian, including the Cisco IOX, Ubuntu, CentOS, Red Hat, Windows 10. So this is the current status of our testbed. Today, you are able to deploy applications on any of these chosen layers if the application is packaged in a Docker environment. And the next step in this tutorial, I'm going to show you how we deploy our application on the IR829, the simple web server application that we just created We are going to deploy it on the IR829, and we're going to see how to do that now. To do that, we need something called the Cisco IOX client. Cisco IOX client is simply a client-side software that translates a Docker-based container into the IOX environment that works with the Cisco operating system. The next step we need to do is install the IOX client. After we have installed the necessary translator, we need to package the Docker image to a Cisco IOX image, and we do that using a simple command, which we're going to look at now. After that, we upload the image to a manager called Cisco Kinetic Gateway Management Module, which is also referred to as GMM. This runs in the cloud, so we have access to all our Cisco routers and switches from the cloud, and we push down the application remotely. The last step I'm going to show you is how do we deploy it finally on the device. Now I'm assuming that steps 1 and 2 have been completed, and IOX client has been downloaded and installed, and now we look at how we use it. So to package an application using the IOX client, we simply say IOX client to call that library. Docker is the keyword, package, and we give it the image ID or image name, and finally the location. Because I'm working in the current directory, which is the same directory I created before, all my files are here, I am simply going to replace location with a dot. Running the command for simple server image goes ahead and creates the necessary file structure that will work on the Cisco IR829 router. Now this packaged Docker image is saved in my desktop and Docker tutorial in a package.tar file. Now if we look at the list of files in that directory, now we can see that the working directory I was in has been updated with 2 new files, package.tar and package.yaml. It also includes the index.html and the Docker file that had the instructions to construct the original image, and this package.tar is a translated image. Now the package.yaml simply refers to yet another modeling language. This is a configuration file that if we chose to tell the machine that will run this packaged image, if we want it to run in a certain way, or have a certain resources, or have certain ports open, this is the file we're going to configure. Because this is a very quick basic tutorial, we're not going to go through that. We're going to see how we can transfer this package.tar file onto our router now. Now that this file has been created, I go on to the Cisco Kinetic platform. The Cisco Kinetic platform offers us a way to look at all our gateways, look at their status, if they're running, if they're down, and look at the containers that are running on top of each gateway. Also, these gateways are supposed to be deployed remotely. We can also see their location, their GPS locations. But for this tutorial, we're interested in jumping to the deployment. So we browse to the applications, and here's where we house all our applications. To add an application, we simply add application, upload the package.tar file, and this package.tar file gets pushed to the Cisco cloud, the GMM, and it unpacks it and prepares it for deployment on the IOX platforms. So now it takes a while. Because it takes a while, I have created video tutorial instead of a live demo to speed up the process. And now we can see that a simple web server application is now visible on my applications catalog, and I can simply tick it, select install, and here is where I select a configuration profile for my application if I haven't done it in the YAML package.yaml file. So I select a profile to give it certain resources, to give my container certain resources. So I have selected a small profile, which is the minimum. I have selected which router I want to deploy it on, and I simply click install. Now the application is being installed on the router. It's being pushed from the cloud to the router. And if we go to our gateways, select the dev gateway, we can see that the application deployment has started. This is a container. It's not an image anymore. This container is now running, and the web server is accessible at the IP address of my router with port 80 chosen because this web server has been configured to work on port 80. This is a very simple application that has been created for the purpose of this demo, but similarly, any other application that includes very basic analytics, very basic aggregation of data, or simply data flows can be programmed and deployed on the Cisco testbed in any of its layers due to compatibility with Docker. Finally, I leave you with a cheat sheet that summarizes all the commands that might be useful if you were to learn Docker and use it in your work.